Hi guys, I'm going to do the lecture on as a video, and this is a continuation from the last class. And then I believe that we looked at the first diagram over here, and yeah, so this part was done, and I think I have to use a different color. All right, so let's look at the second section over here. It says now your friend pushes down on the box with a force of 40 Newton, and this is the picture, the corresponding picture. Okay, so let's have a look and then follow the steps. I said that when you first of all you can draw the box and then you can collapse everything to a dot. So this is part B, and here I am collapsing the box onto a dot, and there you have F of G, which equals to mass times G, and then you have the normal force Fn, and then in addition to that there is a 40 Newton force. Since it is not enough to no space, I am just going to make this dot a little bigger, and then I am going to draw the 40 Newton force. Now as a habit, it's best that you draw your positive x direction, because we measure all the angles with the positive x direction, and there you have the y. Now at this point you can see that there are no forces along in any of these quadrants. First quadrant, second, third, fourth, we don't see any forces pointed at or in these quadrants. All what we have is either along the y direction in the positive direction or in the negative direction, right? So we can set up the table if you like, and then you can call this sum of f the y table, and I'm going to set that, and the box is not going anywhere, therefore the acceleration equals to 0. And then here's my positive direction. I'm not calling it positive direction, it is positive direction, but it is not relevant here. This is the y table. This is the y table, and I'm going to write Fn first, and then Fn sine 90, because cosine is for x components. Here we are looking at the y component. So sine 90 equals to 1, and there you have Fn. And then you have 40 Newton force, and I want to take it along y direction. So I write the magnitude, and sine angle is 270. I am not going to go back to all those things we discussed in the last class. I'm just going to take the components. Sine 270 is a -1. So 40 times -1 is -40. And there you have f of g. And I think we know that as a number here. The gravitational force, yes, because mass is given to us as 10. And then Fg along y direction, we write Fg sine of 270 again. So Fg equals to mass times g, and then sine 270 is -1. So you have minus, mass is 10, g is 9.8. So with that information, I am writing the sum of F equals to mass times A along y direction. That's an equal sign. And then we get the summation. So I'm using the blue pen here just to get the sum of all the forces. You see that I stopped the curly bracket over here. I didn't go to this column, because that column does not represent any force. It only has the acceleration along y direction. So I sum the forces along y direction, right? So here's the first force, Fn. Second force, -40, and the third force, -10 times 9.8 is 98. And then this side mass is 10 and the acceleration is 0, so this side is 0. So you have Fn minus 138. There you have Fn equals to 138 newtons. Now if you remember in the last class, when we found the normal force for the first case where you do not have this external force 40 Newton, we ended up having an answer of 98 Newton. And there we directly had Fn equals to mg, and that's how we ended up with Fn equals to 98. And you can clearly see that Fn does not stay as a constant. Depending on each case, Fn changes. And then here we have 138 as our final answer. And one thing that I want to note here is this. Now we did the table, that is true, Y table, but just by looking at the diagram here, you can simply say the sum of Fy equals to, along Y direction we have Fn pointed up, and in the negative direction there is a 40 and another negative mg. Just by looking at the picture, I mean, I did not write sine 90 and sine 270s here. Just by looking at the force diagram, we have one force in the positive y direction, and there are two other forces pointed in the negative y direction, and then the forces are 40 Newton and mg. These are the two forces, right? So you can do that as well, but if you think you are not comfortable with that, then you can set up the table. You can do either. I will be posting another video, and that second video that I am going to post, you will see this method just by observing how the forces are. You are taking the components along x and y directions. Okay, now we are going into the third part, part C, and now this is different from both A and B. Here you have the force exerted, an additional force exerted on the box, and that is 40 Newton, and this 40 Newton is in addition to the normal force that we had earlier, right? So we have two forces now pointed up, and one force, that is the gravitational force, which equals to mass times g. It is pointed in the downward direction. So we follow the same steps as before, and we set the positive x direction, just so that you understand that, you know, the forces are along y direction only. And if you want, you can set up the table as before and take each force. I mean, that's extra work, but that's okay. Let's do this one more time. And then also by observing what's on the picture, since there aren't any forces in the first, second, third, fourth quadrants, since all the forces are lined up along y axis, some are in the positive direction, some are in the negative direction, even without the table we should be able to do this. Anyway, I'm gonna get the Fn. Nothing happened. Fn is Fn sine 90, since we are looking at the y table here. And then we have Fg. Fg also nothing happened. Like before, you have Fg sine 270, and Fg equals to mg. Sine 270 is -1, and sine 90 here is +1, so Fn times 1 there. And then the 40 Newton force is now no longer along the negative direction, right? So these are all y components, therefore I put the y. So this time the 40 Newton force is pointed along the positive direction of x. So the angle that you measure with respect to the positive x-axis in counterclockwise direction is 90. So you have sine 90 there. Earlier we had sine 270. Now you have 40 times 1, and there we have that. And then the acceleration, the box is not going anywhere, so like last time, acceleration remains as 0. Now we are setting up the Newton's law along y direction. Sum of Fy, mass times Ay, and then we put Fn from the table. Okay, let me pick the stuff for the sum, and there you have Fn minus mg. Okay, I think I should pick the white. Fn minus mg plus 40 times 1, right? And then here you have mass times acceleration is 0. So this time you get Fn minus m is 10 and 9.8. Nothing changed from before. and there you have 0. So you have Fn minus 98 plus 40 equals to 0, and this is our last case, case C, and we ended up with Fn equals to 58 newtons. So you can clearly see that depending on the case, depending on how the forces are oriented on the object, the normal force changes. So there is this misconception which says that, you know, Fn equals to mg. Well, Fn equals to mg happened only for the first time when there are no additional forces exerted on the box. This is case number 1, or case A. And the second case, we had an additional force pushing it down, and the third case we have an additional force pulling it up. So depending on the case, normal force changes. So please remember, we need this later when we are dealing with friction force. So when we discuss friction force, you will see that I'm going to write the kinetic friction. I will introduce that again later. I briefly introduced it last time, but the kinetic friction force is given as a constant mu k times Fn. So here you can see that Fn comes back. So how do we find Fn? Well, you are using these methods or Newton's second law along y direction to find the normal force Fn. So please remember, we will be visiting this soon, and we need to know how to find Fn then. Alright, so next I am going to talk about Newton's law of universal gravitation. If you read, this is actually coming from the slides that I have posted on Blackboard. The gravitational force on U is 1/2 of a third law pair. The earth exerts a downward force on you, and you exert an upward force on the earth. We talked about the reaction and action force under Newton's third law, right? Now, when there is such a disparity in masses, the reaction force is undetectable. But for bodies more equal in mass, it can be significant. So here we are looking at two objects, and let's call this mass 1, and there you have mass 2. And these two masses are not just like a person standing on the earth, like, you know, earth and a person type. Here we are looking at one is a planet and the other one is the moon. So the magnitude wise, they are not of course equal, but they are sort of like, you know, comparable, right? Now, when you have a situation like this, they actually exert force on each other, and you can see that this force over here pointed like along the line that you connect them, the forces are pointed out. So I call this F21, and then here I call it F12. The reason I call them is because the force on moon, which we called as mass 1, is F12, and the force is there because of the earth over here, and the second force I called it as F21 because we called mass of the earth as M2. So this is just like, you know, nothing to worry about. I mean, just a way of calling them, like naming them. I mean, I'm not going to go into details of this one, just wanted to show you that these forces exist. And the gravitational, Newton's law of universal gravitation is given by this equation over here. So first of all, I must say I called one F12 and the other one F21. They actually are equal in magnitude. Then if you are wondering about the differences, well, if you have this as M1, if you have M2 over here, then they are pointed in different directions. One is in the leftward direction, the other one is in the rightward direction. Other than that, I actually should draw the arrows of the same length because they are they represent equal forces. Let me try to redraw it. yeah, about the same size, right? So here you have F12, I called it F12, and there I called it F21. Now in the equation over here, this equation, you don't see, you actually see M1 and M2. That's because you have M1 and M2 over here, and those are the two masses. And so the force F is given by the uppercase G. You don't know about this yet. M1 M2 over R square. So if you are wondering about what this R is, then that is actually the distance between these two masses. This is R, and this is an equation which you call as the Newton's universal gravitational law. And then this big G over here is a constant, and it is given by 6.67 times 10 to the negative 11, and the unit is a little bit complex. Like, you know, it's not just like meter second, meter hour type, just like those that we have come across before. It's Newton meter square divided by kilogram. Now let's say that you want to do a small example to understand this better. So this is coming from the slides again. Now here you have two people, like, you know, a woman and a man sitting on a bench, and then you actually think that, you know, there are no forces exerted on them because of their existence there. Well, that's not right. There is a force actually. So this, let me call the woman as mass 1 and the man as mass 2, and the distance between them is R. That's what we discussed. So there should be a force pointed along this way, and we can call the force on the woman as F1 2, and on the man we can call it F21, and we know the magnitude, absolute value, they are equal to each other, because that's what I said earlier. Only difference is that they are the forces are pointed in opposite directions. So if in order to solve this problem, we can write down the given information. Mass 1 50 kilograms, mass 2 70 kilograms, and the problem says that do we have a distance given here? Oh no, it is not given. It just says estimate. So we can actually decide, maybe they are like, you know, about a meter apart. Maybe, since we need an estimation, if we can take R equals to 1 meter. This is just to estimate the force, and then we can plug the numbers in. So here we have the force. It can be F12 or it can be F21. The absolute values, they are the same, and then I write G M1 M2 over R square. So if you plug the numbers in, G is 6.67 times 10 to the negative 11, and then multiplication. If you like to use parenthesis, go for that. There you have 50 times 70, and in the denominator it's easier for us, since I picked the radius as, or the distance as 1. 1 square remains to be 1. So here you will have 6.67 times 10 to the negative 11, and 50 times 7 is 3500, and you can do the multiplication, and you can find the forces exerted between these two people. And I'm not going to use my time to find the calculation here, and this is the answer. That's the force exerted on each other by the other because of their existence. Let me put it there that way. Now you can see that there 10 to the negative 11 is there, and that tells us the force between these two people is extremely small. because of that they don't get, you know, attracted or repelled, well in this case actually attracted, and then, you know, there won't be any collisions because of that. Unlike magnets here, there is no huge force in between them, but there is a force between them. So even in the class when you guys are sitting, like, you know, there are a lot of people around, and because of each person's existence in the class in certain distance away, you actually experience a force, so in different directions in this case, in that case, right? Yeah. Alright, now I'm getting into tension force. Now, last time in the last class, we discussed about the gravitational force, which was pointed straight down, and we called it Fg. And also we discussed about the contact force, one of the contact forces, and we called it normal force Fn, right? So this is what we discussed in the last class, gravitational force and normal force. Now I am going to add on to that, and that is the let me pick a color here. Yeah, so that is tension. Now if there is a block, let's say, and then we are applying a force using a stretched string. It can be a rope but stretched, or it can be even a string, but it still has to be a stretched string. And there you experience a tension force, and the tension force is always away from the object. So here you have the let's say the block is sitting on a table, and there you have a rope, and the rope is attached to the box, and there you have the tension force pointed away from the object in this case. Now if you have, I'm going to call this example 1, and then example 2 I am going to take something like a hanging block. Now the hanging block, there is the block, and there you have the rope, right, attached to the block and the ceiling. So how do we draw the tension force? Away from the object, pointed away from the object, and you call it Ft. And then I'm going to call example number 3, an inclined plane. Remember we were talking about inclined planes in the last class as well. So there you have the box, let's say this is the box, and there is a rope attached to that, and the stretched rope pulling it up, and there you have a tension force exerted on the block, and you call that Ft, and pointed away from the object. Always the tension force is pointed away from the object. Now whenever you see a rope, a string, or like an external force given in this way, you actually apply the force in the direction that I have shown in these cases. You call it F sub T, and T stands for tension, F stands for force. So tension force is what it really means, and always away from the object, along the string, along the rope. Now I am going to take all these things and have a picture like that you can mark all the forces that we know so far. And the box is sitting on a table. So this is an example with 3 forces. Example with 3 forces, and one is F of G, the other one is F of N, and the last is F of T. Now here you have a rope, and there you have a contact surface, right? There, let me put it in blue. This is the contact surface. Now if you are to mark all the forces acting on it, well, this is what we do. First of all, we mark the known, or the one that you can see clearly. This is, there is a rope pointed, and the angle that you measure here is theta, and the theta is measured with the horizontal axis or x-axis. And in addition to that, we have the F normal, the normal force acting straight up, and then we have the gravitational force acting straight down. So this is what is called as a force diagram. So I'm going to collapse this onto a dot, and here's what you see. Normal force straight up and the gravitational force straight down, and this is the x-axis, and the F tensional or Ft tensional force is pointed at an angle theta. So we already know how to take the components. So at a point here like this, sum of Fx should be, you should be able to take sum of Fx, and also you should be able to take sum of Fy, and then we should be able to set them equal to sum of Fx equals to mass times Ax, and sum of Fy equals to mass times Ay, just like that. And if the mass is given to us, if all the forces are given to us, we should be able to find the accelerations. Now if it says, now this is a key point, if the problem says that the block is moving along the table, right, it's not going anywhere but along the table, then you can have a non-zero acceleration but along x direction, but definitely it is not moving along y direction, therefore, or it is not going upward direction, therefore you can say Ay equals to 0. I mean, here let me put it in a better way. Block is moving along the table in the positive x direction, let's say positive x direction, and in that case you understand that the acceleration along the table along the x direction can be a non-zero value if it is speeding, but definitely there is no y component for the acceleration, because clearly the problem says the block is moving along the y table. So this is a key point to remember. Not just remember what is given, just remember when an object is moving only along x direction, the y component of the acceleration is 0, and that actually makes our lives easier, especially when you use sum of Fy equals to mass times Ay. So you can write mass times 0 on this side. What about Fy? Well, Fy, you can set up the table, and you will, I'm just going to write what you get when you use the table. Check this out on your own. Fn will be Fn sine 90. So Fn sine 90 will be Fn. And Fg will be Fg sine 270. That will be negative Fg. And the last one, Ft sine theta. So when I do this, I always take all the angles with respect to positive x-axis, and everything is measured in the counterclockwise direction. So here you have Fn minus Fg plus Ft sine theta, and the other side, since Ay was 0, we end up with a 0. And then by analyzing this equation, you should be able to measure something that is not known. For example, if theta is given to you, you can find Ft if you know Fg and Fn. Now we can't stop there. We have to write the second equation also. Sum of Fy equals to mass times Ax, and there you have Fn cosine 90. So you will see that it is cancelling out, and there you will have Fg cosine 270. You will see that also gets cancelled out, and then last one would be Ft cosine theta. The whole point of learning how to take the components and being able to sum it up, and that's why this is why we did that. And then here you have m times a acceleration along x direction, which is non-zero, and then you will see that that term cancels out. Check it out using your calculator, and the only remaining term is ft cosine theta and mass times a acceleration. So depending on what is given in a given problem, we should be able to solve this without much trouble. So I'm going to do a simple example from the assignment that I posted on Blackboard. And the only thing that I am left to teach you is friction. And after looking at a couple of problems, I will get into friction.